Today, I'll be talking about converting and inverter graphs to CNF formulas. We use SAT solvers all over the field of hardware model checking. Almost everything we do has to do with either calling a SAT solver or behaving like a SAT solver, or both. So I want to show a brief explanation of how does one convert a graph that is meant to model some hardware architecture and turn that into something that has to do with logic and the connection between them. Let's get started. First of all, and inverter graphs, I've made a video about this. I think this is I've put in the link here, so you can go and check out what I did there and what an inverter graph is. It's just basically a way to model hardware that uses only AND and NOT gates and latches and the ground and inputs. It's a simple way to represent a circuit. If you want to learn more, I'll put a link in the description, and you can go and see another video that I made about this. So, what is a CNF? It's conjunctive normal form. It's basically a way to write a formula in Boolean logic that is basically AND or conjunction of multiple things. These things, we call them clauses. And a clause is basically an or a disjunction between multiple things. These things are called literals. And a literal is just a variable or its negation. All right, we'll see an example in a bit. That's basically what we're talking about. If you're familiar with logic, this would not be new to you. And if you're not, it's basically like a form of AND over things. These things are OR over things, and the things that they're OR over are called literals. We'll see an example in a bit. Before we continue, I just wanted to talk about the DMX file format. It's a file format to write CNF formulas. It was developed for SAT competitions. It's an easy, like, line separated file, and these lines can either be comments, and they typically start with they always start with C. You can have multiple comments in the same file. You also have a header. There can only be one header, and it starts with the letter P. And it contains the amount of clauses that will be in the CNF, and it contains the highest variable used in the CNF. And the clause line is basically one line that contains negative or positive numbers. If they're negative, it's a negated variable. If it's positive, it's a non-negated variable, and it ends with 0. Okay. Typically, DMX files end with a .cnf ending. This is a CNF. This is a DMX file. It starts with 2 comments, as you can see here. Example 1 CNF, and another comment. Some variables may not be used. Then we see that we have the CNF starts with a P. This is the header. 4 is the number is the highest variable that will be used, and 2 is the amount of clauses that are in the CNF. Similarly, we have another CNF, just with the highest variable changed to 3 because we didn't use 4 here. It was designed this way so if a C program is reading it, it would know how much to allocate just by reading the header. So it would know how much to allocate for clauses and how much to allocate for if you have some sort of histogram for variables, then you'd know how big the histogram would need to be just by reading the header. And then you would read the clauses one by one. And here we have another CNF, and it ends with a C. It's just an empty comment. Now, just to clarify, what for example this CNF is saying, it's saying either 1 or 2 or not 3. That's the first clause, and not 2 or 3. So that's the layout that we're talking about. This is the logical formula. In order to satisfy the CNF, you have to satisfy each of the lines, which means satisfy each of the clauses. And to satisfy a clause, you only need to satisfy one thing that's inside of it. Okay. Now, how do I translate AIGs into CNFs? First of all, why do you even want to do this? Because we use SAT solvers to ask questions about the graph, about the circuit, and to be able to express some features about the circuit. We translate by simply giving a variable to each node in the graph. And by that encoding, that mapping between node to variable, we can then refer to multiple things in the graph, and we can encode AND gates, and it will all make sense. So that's it. We map each node to a variable, and then we go from there. Add to CNF, let's start by taking an example. So every node is represented by the variable number that it's equal to its signal. This is a design choice that I took in my translator. It doesn't have to be the case. You could have given any other mapping, it would have been fine. The ground has no variable number because 0 is not a legal variable, so it cannot be in the CNF. A state, what we refer to as a state, is an assignment of the variables that are given to latches. For example, if the latches are signals 4, 5, and 6, then their variables will also be 4, 5, and 6. And a state is basically just what do you give to the variable 4, what do you give to the variable 5, and what do you give to the variable 6. Two input AND gates can be encoded using 3 clauses. We'll see that in a bit. And the variables that represent the AG after one clock cycle are basically the same variables, just shifted by the greatest signal number. Let's take this AAG, we saw it in another video, in a previous video. And first of all, give a variable to each node according to its signal number. We just number them like they would be in an AIG file. The ground needs to be 0, but we don't give a variable to 0, so it's okay. The input needs to be 1, this latch needs to be 2, this latch needs to be 3, this latch needs to be 4, and this latch needs to be 5. And then the AND gates would be, I would say this would be 6, this would be 7, this would be 8. We could have given another order to the AND gates, that's just what I picked, okay? Let's assume that 2 is initialized to 0, 3 and 5 are initialized to 1, and 4 is uninitialized. So the initial relation would be a CNF that, if satisfiable, would indicate a possible starting state. What does that mean? Well, I'll present it and I'll explain why it's correct, and then hopefully you'd understand a bit more. So this would be an initial relation. Why? Because if I had an assignment that were to satisfy this CNF, 3 needs to be 1, 5 needs to be 1, and 2 needs to be 0, and 4 can either be 0 or 1, and in both cases that'd still be an acceptable starting latch configuration. Okay, so now we see that if you were to assign this CNF, you give it an assignment, that assignment would make sense in the latches. And vice versa, if you were to give a legal starting latch configuration, and then you create an assignment from that, that assignment would satisfy the CNF. If you were to ask the stat solver, give me an assignment that satisfies this, it would give you an assignment, and that would be a legal latch configuration. All right. Now, encoding AND gates. Let's take an AND gate here and try to encode the variables that go into it and the variable that goes out of it, and just kind of encode the relation between them. If x is 1, okay, the variable z should be 1 if and only if both x and y are 1. That's what an AND gate is. So if x is 0, then z is 0. If any of these two, x and y, are zeros, then z would be 0 as well. If y is 0, then z is 0, right? We need to encode that. And if x is 1 and y is 1, then z is 1. Okay, and you can see we have these 3 formulas. We just need to rewrite them in a way that might look like a CNF. All right? So let's begin the translation. We can convert these 3 formulas to CNF. And then formula 1, we just start off with not x leads to not z. And out of the property of this right arrow operator, this can happen only if either not x is not true, so we don't satisfy this part, or not z is true, which basically means x or not z, and this is a clause. All right, let's see if the other formulas can become clauses, and then we will be done. Formula 2 is very similar to Formula 1. It's just y instead of x. So we use the same logic and we can reach y or not z as a clause here. Formula 3, we start off with x and y to lead to z, and then we do the same logic of what is the property of the right arrow operator, and then we take this not and we lead it to be inside. We do that by De Morgan law, if you're familiar, and this would be not x or not y and or not z. We can just drop the parentheses here, so it's not x or not y or not z. This is also a clause. So in conclusion, we got three clauses that map an AND gate. All right. Now keep in mind, if x is the ground or x is the negated ground, then we can't really have a variable that represents it, but we can simply indicate that y and z have this relation between them in a very similar manner to the logic we made here. So it's something that we are capable of doing. Let's continue on with example 1. This is the graph that we're talking about. This is the initial relation that we saw before. Now the safety property, what a safety property means is that on this output, you'd never have 1. There would never be an on wire here. And so what does this mean? We want to first map the latches, the 4 and 5, to whatever output is, and then make sure that this output is always 0. Okay, so first of all, we add the three clauses that represent the AND gate. Okay, so we see here that this AND gate is taking -4 and -5, and so we plug that into how we represented the AND gates, and we get these three clauses. Okay, and then we just want to make sure that 8 is always 0, so we just add not 8, which is just -8. And that's how you map a safety property. For the transition, we just want to take every number here, every latch, and run it through the circuit once, and then express the relation between the latches before and the latches after. Okay, so first of all, we encode this AND gate. Remember that this is just a 1. So what's basically going on here is we're forwarding the input through. So 7 and 1 are equal, always equal. So these are what 1 minus 7 and minus 1, 7 mean. The same happens for 2 and 6. So we have 2 and minus 6 and minus 2 and 6. These basically mean that this number after the 6 is equal to the number before, and same for the 7 here. Okay. Now that we have those, we just need to tie this wire right here. We need to tie it to this number here after one clock cycle. Now after one clock cycle, the highest variable here is 8. Okay, so 2 plus 8, we kind of shift the numbers forward. 2 plus 8 is 10, so the next state variable would be 10. Here we started by tying 3 and 12. This 3 minus 12 is basically saying that the output of this 3 latch is going to 4. So the next state of 4 it would be 12, right? Because it's 4 plus 8, so it's 12. And so 12 and 3 are equal. This is basically what goes on with these two clauses. They're saying that 3 and 12 must be equal for an assignment to be correct. The same happens with 4 and 5, so we're connecting 4 and the next state of 5, which would be 13. Also, the same happens for 6 and 3 right here. So 3 plus 8 is 11, and we see that we're connecting them right here. And this also the same happens for 7 and minus 10. For 10. 10 is basically the next state of 2, because 2 plus 8 is 10. So then the variable that represents this latch value after one clock cycle would be 10. So we're just saying that 7 and 10 are equal. Let's take a look at another example. Here we take some random AIG file with some nodes that are redacted, and we're going to try to encode it into CNF. Now, the thing that I want you to take away from this example is that it doesn't matter what the graph does. You don't really need to understand it at all. You can just follow the rules and encode it into CNF. we have two latches here, S4 and S5. The first latch, S4, is initialized to 1, and the second latch is not initialized. So the initial relation will just simply be 4. It will have one clause that has one literal that is just 4. As you can see, this is the initial relation. The property, to understand what the property is, you have to first understand what is the output of this graph. And the output is S7. This is not something you could have known from the graph. I'm just claiming it right now. So all we have to do is encode the AND gate that is S7, and then make sure that its output remains 0. To encode it, we only need 2 clauses, because both of its inputs are a negation of S4, which basically means that 7 and 4 are different. So we need to encode that. And then we need to make sure that 7 remains 0. And that we did that right with not 7. For the transition relation, we first have to encode the AND gate that is S10. We do that with 3 clauses. And then we have to first take the next state of S5, so the next state of this latch right here, and that would be 5 plus 12, which is 17. And make sure that 17 is equal to 4 from the previous cycle. So we add 2 clauses that make sure that 4 and 17 are the same. Okay, and then we do a similar thing to the next state of S4, which would be 4 plus 12, which is 16. So 16 and 10 need to be different because we have a negation on this edge right here. And that's what these 2 clauses do. And that's it. We just encoded the transition relation, we made an initial relation and a safety property, and that concludes this example. That also concludes the video. Thank you so much for listening. If you have any questions, I would be happy to answer them in the comments. I also would be happy to hear some suggestions about material or papers that are not clear that you would like me to explain in future videos.